Okay, folks, this will be the first video from section 3.1, and specifically what I want to cover on this first video is what we call the power rule. So we're going to kind of compile some results that we've already seen together, formalize that into what we call the power rule, and then I also just want to discuss the two different types of derivative notation, because sometimes the different notations can be a bit confusing to look at. So first up, I've listed a couple functions here. So just a regular old linear function, basic power function of x. You could call that x to the first if you like, x squared, x cubed, x to the fourth. So just kind of to reiterate the pattern that we noticed in class together. Okay, we had found all these derivatives the long way using our limit definition, which is really the definition of what a derivative is. And that was this: the limit as h approaches 0 of our f of x plus h minus f of x all over h, right? And remember, without the limit here, what we're really looking at is the slope of a secant line connecting a particular x value with a nearby x value, which we called x plus h. And so we've got those slopes of those secant lines. We let the secondary point get closer and closer to the original point by letting h go to 0 in our limit. And then we had some different techniques where we had to solve these different limits the long way, and we got our results, all right? So we're not going to be going through this in this video, just sort of compiling the results that we got and trying to see if we can identify a pattern, and once we get a pattern, try to sort of establish that as a rule using our different derivative notations, okay? First one we looked at in class using that definition was x squared, all right? And we went through the whole limit, and we found out that our derivative for that was 2x, all right? Coming down the line, when we did x cubed, what we saw was the exponent of 3, just like this exponent 2 kind of appeared out front. We ended up with a 3x, but that x still had an exponent on it, and what it was, the new exponent was a 2, so it was 1 less than this 3. All right, and so throughout these different examples, I want to make sure that this pattern is consistent. Here we started with x raised to the 2. The exponent 2 appeared out front like that, and then I've got a single x. That single x is really x to the first, so that kind of works out as well. All right, x to the fourth power, we saw, I can't remember if we worked this one out, but this one was on the, it was one of the problems you didn't have to do on that problem set 1, but maybe you went through it. And if you go through it, you're going to see that this pattern holds up. The 4 appears out front, the x, and then we had the 3 out there, all right? And when we did this, the slope of just the line y equals x, or the derivative of that line, rather, we found that the answer was just 1. And I kind of argued that in a couple different ways. We went through our limit definition with that function, and that the limit of 1 came out pretty quickly. But also remember this, if we graph this function f, it's just a line, oops, I kind of missed the origin right there, but just a line passing through the origin with slope of 1. Right? And so if the slope of this line is 1 everywhere, then the derivative function, which tells us the slope of this function, should be a constant, should be whatever that slope is, and we got 1, all right? If you're thinking about how this rule might work for this function, let's think I've got x to the 1. So if I brought down the 1 as a coefficient, I could do that. And if I wrote x and then decreased this power by 1, because that's the pattern that we've observed, I would end up with an exponent of 0, all right? And you can actually use that if you like, because what is that all equal to? Well, something x raised to the 0 is 1, and then 1 times 1 is 1, right? So we get that result kind of using that little power rule of bringing the exponent down and then decreasing the exponent. Seems to work with all of these examples, all right? So typically, you don't see that notation there with the 0 and 1 exponents, but you can do that if you like. All right. So yeah, so we had this rule, and let me look at 2 more examples where we actually saw this rule working, and then I can state the rule formally. So we looked at, let me call it g of x. We looked at the reciprocal function, 1 over x, and then we also looked at, let me call this k of x, was the square root of x. All right. And so again, we did these through the long way using our limit definition. We went through the process, let h go to 0. We had to cancel out, do some special tricks, right? Here we had to combine some terms. Here we had to rationalize the numerator, so we had a special technique. But what we got was that if g is 1 over x, and remember 1 over x is this, x to the negative 1 exponent, then what we found was that the derivative was, we kind of got x to the, we got this, negative 1 x to the negative 2. So let me talk my way through that. If this exponent, negative 1, comes down out front as a coefficient, it lives right there. And then if I take negative 1 here and subtract 1, decrease it by 1, I would end up with a negative 2. And this is actually what we got, but we rearranged it a little bit. The x to the negative 2 I don't like the way that looks. So I want to put that guy in the bottom as x to the positive 2, and then this minus 1 lived up top like that. All right. So again, we found this kind of the long way using our limit definition, but if you try to take our shortcut as far as bringing the exponent down out front, then decreasing it by 1 to get your new exponent, it does match up with what we found using the limit definition. And the same thing happened over here. All right, so this square root is the same as a 1/2 power. Okay, so again, let me talk my way through the process of the shortcut using the power rule. If I take this 1/2 and bring it down out front, I'm going to get 1/2. Then I'm going to take the x and I'm going to write a new exponent, which is this exponent, but decreased by 1. So subtracting 1. And if we take 1 away from 1/2, we end up with a negative 1/2. All right. And the way we can clean this up, again, typically we don't like negative exponents at the end. So we kind of want to move that x, move that variable around to the other side of the fraction bar to create a positive exponent. So this x right now lives up top. So let's move it down to the bottom, down there with that 2. And then by doing that, I've created a positive exponent on that x. All right, and this numerator of a 1 placeholder still lives up there. Okay, and that's fine. That's a good representation of our derivative here, which I'm going to call k prime of x. But another way to represent this is this x to the 1/2 power. Let's convert that back to a radical. And usually on paper, I think that looks pretty nice. If your original function is in radical form, maybe express your derivative also in radical form. So something like that. All right. And again, so we found this together in class using the limit definition. So I'm not claiming that this power rule automatically works necessarily in its own right, but if we look at all those 6 functions that we've just put up on the board right now, it always seemed to work out that this little shortcut works. Okay, and in fact, it does always work when we've got these power functions. We can say x raised to some kind of exponent. Here we see it holds up for negative exponents. It holds up for fraction exponents. So it's a pretty versatile rule. All right. So let me state that formally using some derivative notation. All right. And so all the derivatives that we've done together so far, either in class or in these videos, I've been using what we call this prime notation. Right. We call this f prime of x. And so that's one style of notation. What you notice with all these examples, if you want to express that you've got a derivative using the prime notation, you kind of either need to write down or state some kind of if-then statement. In other words, you have to say if the original function f, and what I'm going to write here is x to the n. Okay, so in other words, x to some exponent, n, some what we call a power function. Then sort of the conclusion to this if-then statement is then the derivative f prime of x is equal to, and so I'm going to write that using this rule. So let's just think through what we did with the rule. The rule says take this n, bring it down out front. So whatever exponent we had seemed to appear as a coefficient out front. So that means I should get n as a coefficient. And then multiply that by, still got a variable x, and then what the new exponent became was the original exponent minus 1. Right, we subtracted 1 from the original exponent. And so n times x to the n minus 1, there we go. That's our power rule. So again, as an if-then statement, the power rule says if f of x is some kind of power function, x raised to some exponent, then the derivative will always have this form. Alrighty. There we go. So, cool. That's cool. That's our power rule. So from here on out, if you are asked to take a derivative, probably not breaking out the limit definition and doing it the long way, unless it's the first time we're exploring a new function and we might want to figure it out what it is. Or when we delve into things like trig functions, which are not power functions, right? They're not expressed this way. Then we might have to rely on the definition. But we can take this rule for granted for a lot of functions, so that's pretty nice. The rest of this section is devoted to fleshing this rule out, combining it with some other rules so we can take derivatives of polynomials easily. But before I go there, I want to talk about this concept of the different notation, okay? So the history lesson behind this, sometimes kind of interesting, but you probably heard of Isaac Newton back in the day, right? Mathematician, physicist, right? He came up with the idea of gravity, things like that. So he was a big powerhouse. He studied calculus. He's sort of considered one of the creators of calculus, or the forefathers of calculus. And this notation is sort of attributed to him. So he used something similar to this, sort of like a prime, or I think he used a little dot, but it was something similar to that, some kind of augmentation on your original function right there to express his derivatives, okay? So he was from England. On the other side of the English Channel in Europe was this guy named Leibniz. And he was also a sort of a discoverer or an inventor of calculus, you could say. He was kind of working independently. Him and Newton were sort of rivals. They kind of had they accused each other of stealing each other's work. It was kind of a big thing. But anyway, Leibniz came up with his own notation, which I just call D notation. Okay, so D notation is helpful sometimes. So sometimes it's kind of a shortcut, and so you'll notice it a lot in WebAssign. They use it. Some students were thrown by some of the notation. I could tell a little bit. So let me just show what it is and what it means. And so one nice thing about the D notation is it's a little bit more concise in the sense that I can tell you the original function and then equal to sort of the derivative all in one statement instead of this if-then statement. All right. In other words, if I tell you here the derivative of some function f is this, right? N times x to the n minus 1. But what was my original function? I don't know, right? I'd have to sort of undo this rule to figure out what the original function is, unless I'm specifically told by this if-then statement. So the D notation, then there's some variations on that, but let me hold off. You might see this often, d over dx. Okay, so that looks sort of like a fraction, and that's actually a plus side to this notation, is it kind of behaves like fractions at times. We'll see when we get into the chain rule. But the way I read this is the derivative. So this d, I state out the derivative, and then this d kind of I just say with respect to x. And all that means is with respect to the variable x. That letter right there is what I'm treating as the variable. That little tidbit comes up, becomes more important later when you're dealing with multivariable calculus, when you have x's, y's, z's, and you want to know what you're taking the derivative with respect to. But for the most part, this is what you'll see. If I have a function of t, you might see d dt, right? So some physics problems or different word problems might vary the variable, but this is our notation. So this means the derivative with respect to x of my function. So the derivative with respect to x of a function that looks like this, x to the n, is equal to, and then on the other side, then I just write the derivative, right? So I can just write n times x to the n minus 1, okay? So a lot of the rules, if you browse through the textbook, are going to be written in the D notation, right? Because this little line of information says the same as this if-then. Here I have to tell you what the original function, I'm naming it f, but it's x to the n is my original function. Here that's just written right there. And then I'm naming the derivative f prime, and then I'm telling you what that's equal to. Here I'm just saying the derivative of this function is this function, right? So that's kind of how you read that. All right. There are some variations to the D notation, so maybe I'll mention that. If I've got f of x, sometimes we call that y. Okay, so I could say y is equal to x to the n. That means the same as saying f of x is x to the n. Okay, so sometimes I interchange those things. So if we've got a function, so you might see this, the derivative with respect to x. Sometimes you might see either this y up top right there, so that means the derivative of y with respect to x, or you might see the derivative of f with respect to x. So sometimes whatever the name of the function is will live up top there with that top d. So you might see those. Often you might also see something like this, the derivative with respect to x of f in parentheses like that. These two things mean exactly the same thing, okay? And then you also might see the function written in there. So if I say the derivative with respect to x of x to the 9th power, right? So you can include a y in there, you can include the f as the title of it, you can actually have whatever our rule is just filled right in there. So all the different variations. And so what is our answer here? Well, the derivative with respect to x of x to the 9th, according to our power rule, is 9x to the 8th. All right, there we go. Maybe I'll do one more example with some kind of negative exponent. Let's say the derivative with respect to x of x to the negative 7 exponent. How would I express that? Well, that's going to be negative 7x and then decrease the new exponent, or decrease it to form our new exponent of negative 8. And typically what you'll do there is put that x back to the bottom as a negative 7 over x to the 8. All right, so no big deal. A couple of exercises with our power rule, and then there's those two different notations. Okay, so I will backtrack back and forth between both notations throughout the course so we become comfortable with them. But there we go. So let me wrap this up. This video, I will continue with some other rules that are discussed in section 3.1, and we'll go from there.